why on earth would we want to do this? So one answer is, now adding a new shape is easy. If I want to deal with hexagons, I don't have to go and modify the existing procedures at all. I just write one new procedure, make hexagon, that has all the formulas for hexagon in it. So if I'm adding a lot of data types and I'm not adding a lot of operators, this might be the way to go. Conventional programming, it's easy to add new operators. You don't have to modify any existing code. You just write a new operator procedure. And this is the opposite. But a much more interesting answer about message passing is that we're going to see next week that message passing is at the heart of something you've heard of and maybe used called object-oriented programming, which is the next big programming paradigm. So this is something we have to understand as a precursor to that. Who's used object-oriented programming before? A lot of you. Who knows anything about how it's implemented? How, you know, they write a Java code. My TAs do, OK. That's good. So even those of you who used object-oriented programming before are not going to be bored as we start exploring it next week, because we're going to teach you how it's implemented. It actually turns out not to be very mysterious. So one of the goals of this course is to demystify the different programming paradigms and help you understand how they work. OK, so that's message passing. The next thing we're going to do is go back to data-directed programming for a bit and talk about a problem that we've so far swept under the rug, which is a lot of times you have operators with two operands. Like, for example, minus. I'm choosing minus rather than plus because it's non-commutative, so it makes the issues a little clearer. So let's say I want to add a minus column to this table. I'm going to leave these blank. Squares and circles, you don't do minus on. But what we do minus on is numbers. Numbers, for purposes of today's discussion, come in 4 flavors. Integer, rational, real, and complex. OK. So if I have 4 kinds of numbers, how many rows do I have to add to the table? It depends how I do it, is the answer. The most straightforward answer is 16. Because there's nothing that says that the 2 operands are going to be the same type. I can do integer minus integer, integer minus rational, integer minus real, integer minus complex, rational minus integer, rational minus rational, rational minus real, and so on. 4 kinds of first operand times 4 kinds of second operand is 16 lines we have to add to the table. And furthermore, the labels over on the left column here can't be just integer. We have to say what both of the types are. So we're going to start using lists instead of words as the label for the rows of this table. So we're going to say something like integer, integer. And the next row might be the list integer, rational, and so on. OK? 16 of these down to complex, complex. If we do this, of course, we're going to be uniform in the way our table works. So we're going to use lists even for the operators with 1 operand. So that our operate procedure, which in the book is called apply generic and works for this 2 operand case, has a consistent theory about what it's looking for. OK, so if types are these words, integer, rational, real, complex, and we put them together in a list. That is called a type signature. And those of you who've used languages that call themselves object-oriented but don't believe in message passing will be familiar with that term, that a procedure that you write has a type signature, which is all the types that you declare for all the arguments of that procedure. Okay? So that's a type signature. It can be, it could be 3 operands. The system is extensible to solve any problem. By the way, speaking of numbers of operands, there's another little table. In the literature, mostly, you will see something with 1 operand called a unary operator, something with 2 operands called a binary operator. That's what almost everybody calls them. The problem with this nomenclature is that you all know that binary means something completely different in the context of computers. Right? It means 1s and 0s. And there's nothing about an operator like plus that has 2 operands that has anything to do with 1s and 0s. You might not know that unary also has a similar related meaning in computer science. You might not know that because base 1 seems like a strange idea, but there actually is such a thing. They're confusing. And so, cool people call these monadic and dyadic operators. These names were proposed by Ken Iverson, who invented the important but obscure programming language APL. And they're great names, and they don't have any other confusing meanings. OK, so now we're doing dyadic operators. And so we have these type signatures. So just for minus, we need 16 of them. And if we want to do plus, minus, times, divide, that's 64 cells in this table to keep track of. That's a real pain in the neck. And people mostly would rather avoid that kind of work. And we can avoid that kind of work if we're observant. And we notice that numbers have a special property. Namely, here's the integers. All integers are rational. Right? So the integers are a subset of the rationals. All rationals are real. Lots more reals than rationals, but every rational number is a real number. And furthermore, oops. Every real number is a complex number, right? Now, notice, by drawing this chart in this way, I have done something that many programming language designers don't seem to understand. So they think that 3 and 3.0 are 2 different entities. But that's not true. 3.0 is an integer. Maybe it's represented differently in the computer, but that's the computer's problem, not yours. Mathematically, 3.0 is the same number as 3. And your language ought to think in those terms. Because The purpose of computer science is to enable you to solve problems with computers without thinking about computers, without knowing anything about computers, just thinking in the language of the problem you're trying to solve. So that's sort of the forward march of computer science, is you having to think less and less about how they represent things inside the machine, and instead spend time thinking about the problem you're trying to solve.